I welcome you all to the online session of Strength of Materials 4th semester. And today we will be seeing stresses on helical springs. The main content of today's presentation are objective, introduction on helical springs, maximum shear stress, the spring constant, followed by a sample problem, review question, and conclusions. The main objective after the completion of this lecture, the student should be able to define helical spring and to understand the torsional stresses in helical springs, and this will provide a basics of mechanical spring design in the following semester and to understand about the spring constant. A spring is an elastic member used to connect two bodies or two parts of a machine. The main functions of a spring are to exert a force, for example, a valve, and to absorb energy resulted from shock or vibration, and to provide flexibility. The most important thing in analyzing any helical spring is the wire diameter, that is how we can able to make a helical spring. Normally the helical springs are made by cylindrical wires wound over a mandrel, and d is the wire diameter and is expressed in millimeters, and capital D, that is the mean coil diameter, and N is the total number of turns, and F is the axial load. It can be either compressive or tensile, and it is expressed in newtons. Due to this axial load, the helical spring is subjected to torsional shear stress described by Newton per mm square, and it is due to this force. X is the spring deflection, and capital L is the free length of the spring, and K is the spring constant, that is Newton per mm, and the elastic modulus, that is the shear modulus, that is described by Newton per mm square. So these are the meaning of the symbols, or these are the few symbols that is characterizing a helical spring design. Now let us consider a spring of wire diameter D and coil diameter D subjected to an axial load F. The torque T acting on the spring is given by F multiplied by capital D by 2. If D is the wire diameter of the coil, the polar moment of inertia, that is J, is given by pi d to the power 4 divided by 32. The shear stress in the spring wire due to torsion, we are assuming a pure torsion, the tau is given by T into R by J. If you plug the values for T, R and J, we will be getting the maximum shear stress due to the axial load is given by 8 FD divided by pi d cubed. Now consider the cross section of the spring. That if you cut the cross section, we will be able to see a circular cross section, and if you pull the closed coil helical spring, the wire tends to twist or rotate like a shaft, and due to this force the spring can be moved down, and this movement is described, axial moment is given as x, and this angle of twist, that is theta. And considering the spring as a whole, the value of angle of twist will be very small, and axial displacement that can be found that x is given by theta into d by 2. And while studying the shaft torsion in shaft, we have derived the torsion equation, that is T by J equal to tau by R equal to G theta by L. And if you substitute the values in this equation, we will get W into capital D by 2 divided by pi d to the power 4 equal to tau by R equal to G into theta. We can substitute as 2 into x by d, and L is the length of the wire, that is pi d. Pi d is the circumference and pi d is n. N is the total number of turns in the spring. So if you equate the first term and the last term in this equation, we will get the capital W by x, that is given by G d to the power 4 divided by 8 d cubed n. And this W by x is a constant, and it is a very important characteristics of a spring design, and it can be called as a spring constant, or it is also called as stiffness of the spring, and it is defined as the load per unit deflection. And we have seen that maximum deflection tau max is equal to 8f d cubed by pi d cubed, and the spring constant W by x is equal to G d to the power 4 divided by 8 d cubed n. And we don't need to remember all these formulas by heart. If you are able to understand the torsion equation, only thing you need to substitute the values of the torque and J. We will be able to get all the values that is for the helical spring design. Okay friends, now we will see a sample problem in helical spring. And the question is given by a closed coil helical spring is to carry a load of 5000 Newton with a deflection of 50 mm, 50, and a maximum shearing stress of 400 Newton per mm square. If the number of active turns or active coils is given by 8, estimate the following: A. Wire diameter, B. Coil diameter, and C. Weight of the spring. Assume the shear modulus is given by 83,000 Newton per mm square, and the density of the wire material is 7,700 kilogram per meter cube. So this is a straightforward question. So only thing first you need to write down the given data, so we can see what are the load, that axial load that is given by 5000 Newton, and the deflection due to this axial load is 50 mm. The number of active turns, that is 8, and the allowable shear stress, maximum shear stress is 400 Newton per mm square. So from the torsion equation, that is T by J equal to tau by R, we substitute W into d by 2 divided by pi d to the power 4 divided by 32 is equal to tau divided by d by 2. So first we need to calculate the value of wire diameter and the coil diameter. So from this equation, if you keep d in the left hand side and the remaining terms in the right hand side, we can write d equal to 400 is the shear stress divided by small d by 2 into pi d to the power 4 divided by 32, that is J, and into 2 by W. And if you rearrange the numerator and denominator, we will be getting capital D, that is the coil diameter equal to 0.0314 d cubed. And we already derived that the spring deflection, that is x is equal to 8w d cubed n divided by g d to the power 4. If you substitute the values for x is equal to 50 and w is 5000 and d we have already seen, d we can substitute as 0.0314 d cubed, the whole cube, multiplied by 8 divided by 83,000 d to the power 4. So in this equation there is only one unknown, and if you are we can solve this equation and we will be able to get the answer, that is the wire diameter as 13.32 mm. In design practice we can take the next higher value, say 14 mm, and if you substitute the value of D in this equation, that is D equal to 0.0314 d cube, we will get the coil diameter as 74.2 mm. So we will got the part A and part B, and finally the weight of the spring. So in spring design, if you want to estimate the cost of this material, we should able to analyze what is the weight of that material. So weight of the material is nothing but the volume multiplied by density. So volume is given by base area into height. Height here is the length of the spring. So base area is pi d to the pi d square divided by 4 into pi d into n. N is the total number of turns and rho is the density of the material. And if you substitute all the values in this equation, we will be getting weight. That is the weight of the whole spring material is around 2 kilogram. And if you know the weight, and it is quite easy to calculate what is the cost, what is the material cost of that material. Here I have provided few sample 2 marks questions, and I do understand that the list is not sufficient, but you can read any textbook, that strength of material textbook, to find more 2 marks questions. Here I have given 3 sample questions, and I request all you to go through these sample questions. Now I am going to conclude this lecture, and I hope this was helpful, and this after completion of this lecture you should be able to understand what is a helical spring and what are the objectives and what are the stresses that is acting on a helical spring, and the concept of spring constant, and this is a stepping stone for the mechanical spring design. Thank you for watching this video, and please do contact if you have any doubt through phone, email, WhatsApp.